Hello, do you hear me?
Yes, sir. Can you able to hear us?
Yes, I can hear you.
Sir, your audio video control and screen share options are enabled, right?
Uh, so just a minute. So Zoom has changed a bit. So this thing,
Yes.
video, you cannot see my I mean, the video is not on, right?
Not on, sir.
Uh,
Can you
can you
just turn it?
can you enable, because I saw the request for the audio. Audio I can
Hmm.
see it here. Video, where is it?
1 minute, sir. I'll just find.
Yeah, you can from your end also.
Sir, recently you have received last mail, no? With that link, if you join straight away, everything will be enabled for you.
So this one only, right? This
Uh,
this link is correct, yes?
so the link is correct, but the panelist link is the last mail, today's mail you may have received today's
Uh,
email from
yes.
Karunya.
So I'm
One
joining.
special mail.
So yeah, at 2 p.m. right today. So
Yes, sir. Yes, sir.
yeah, I'm joining with that only. Okay, let me again open this one. Yeah, I think this is the link. Yeah, I have opened.
Uh, okay, sir.
So you can yeah, this is the link I have opened. So
It will be okay. This one will be disconnected, and you can join with that.
no, this one is the link that I received, which I have joined actually.
Okay, sir. 1 minute. Then I'll.
You just have to give me the presentation rights, and that's all. Just
1 minute, sir. 1 minute. 1 minute. I'll call the technician to enable that. Uh,
yeah. Now I think it's okay.
yes, sir. Yes, sir. Good evening, sir.
Good evening.
Thank you for joining, sir.
Yeah.
We'll start the session.
So
Ebenezer Jangam sir is also here. Sir, can you just sir, can you just unmute your video, Jangam sir?
Yes, madam. Can you hear me?
We can hear you.
Yeah, we have a power cut here, so light is
Okay,
not
fine, fine,
present.
fine,
So,
fine. Okay, okay, sir.
okay.
We'll start the session. Good evening,
evening, sir.
everyone. On behalf of the Division of Artificial Intelligence and Machine Learning, Karunya Institute of Technology and Sciences, Coimbatore, I welcome all of you for the Day 4 Session 1. Today's session will run from 6 p.m. to 9 p.m. I would like to read the instructions for participants. There will be 2 sessions today. Only one feedback form need to be filled at the end of the day. For the feedback form includes the feedback related to both sessions. So at the end of the session, end of the second session only, feedback link will be shared with you. So kindly note down your participant ID as usual from the email communication. So if there is any technical queries, kindly post it in the chat box during the session. It will be addressed at the end of each session. Now I would like to introduce the resource person for today's session one. He's Dr. Sandeep Kumar Singh from IIT Roorkee. Sir is an assistant professor in the Department of Electronics and Communication Engineering in IIT Roorkee, Uttarakhand, India. He completed his bachelor's degree in Electronics and Communication Engineering from Sastra University in 2010, followed by a master degree in Electrical Engineering from IIT Madras in 2014. He completed his PhD in Optical Networks at the Technical University Braunschweig, Germany in 2019. Before joining IIT Roorkee in 2023, he gained valuable experience as a research scientist at the German Aerospace Center DLR from 2019 to 2021 and as a postdoctoral fellow at the University of California, Davis, USA from 2021 to 2023. His research interest includes terahertz communication, optical data center networking, quantum networking, and system design with a focus on analysis, algorithms, and machine learning. Dr. Sandeep Singh has been recognized with several honors, including an outstanding paper award at the MIPRO conference in Croatia in 2016 and a DAD, a German Masters Exchange Program Fellowship from 2011 to 2012. Dr. Sandeep Singh will be sharing his experience with us today on the topic quantum internet opportunities and challenges. Welcome, sir. Now you can take over the session.
Thank you so much,
Thank you, sir.
Dr. Jemima, for inviting me for this faculty development program. And it's my pleasure to present the talk on quantum internet opportunities and challenges. Let me share my slides. Okay, so you need to give me the rights, send request.
Yes, sir. Yes.
Okay.
So now it's enabled.
Yeah, so do that.
So can you share your presentation now?
Yeah, I can do that. I can.
Yes.
Let's see.
Click on the share button and you can share.
Yeah.
Yes, sir.
So,
Yes, sir. Yes. We can able to see your screen, sir. You can go for presentation view. Yes.
okay, that's great. So thank you again. So let me go to today's agenda. So in today's presentation, I will talk about the motivation and brief overview of quantum communication and networks. I will define some terminology regarding the quantum mechanics, different technology that have to be used to enable the quantum internet, and what are other applications as well for the quantum mechanics or quantum science in general. And just one thing I would like to mention. So if any participants, anyone have questions, so please you can write in the chat, and maybe Dr. Jemima, you can point it out, or if I get any notification, I can maybe stop a bit and answer your queries. So feel free to answer questions so that if anything is unclear, yeah, please stop me that time itself, no problem. And then after introducing the quantum internet, then I will kind of also introduce some challenges and what are the layered architecture. And I little bit assume that some of you know the computer internet, like classical internet architecture or computer networks architecture, and what I have done so far and what is my current research as IT Roorkee, that hopefully if time permits, I will introduce that. So I believe I have time until let's say 7:30, but including question and answer. So, okay. So if you look at the classical internet development, let me enable the pointer so you can see it better. Pointer here with the pointer. Okay. So it all started way back in 1940s with the vacuum tubes and the transistor coming in around 1960s. And then the integrated circuit development came around during that time, 1960s and 70s. The US ARPANET, which has now become the DARPANET Defense Agency for funding. So they started 5-node network, and internet began actually from this ARPANET project. And the idea was, can we transfer, let's say, our compute messages from or email from the computer from one node to another node? These nodes are located, geographically. And after the successful development of this network, then similar development happened around other side of the Atlantic in the UK. And idea was, can we interconnect these two different networks? And then from that time, internet came into the existence, so-called internet. So that's interconnected networks. So how can we interconnect different networks, right? That's internet. And in 1984, Macintosh computer came, and it kind of, changed the world completely. After these initial developments in the hardware, the second round of development was related to the software. So in software, some of you may aware that TCP, this Transport Control Protocol over Internet Protocol, it was developed in 1973 by Vincent Cerf and his team. Vincent Cerf, ironically, he was also the undergrad student for this ARPANET project. So he gained some knowledge during this ARPANET project, and then when he joined a professor at Stanford, so he and his team developed the TCP/IP protocol. And following that, Internet protocol came, Ethernet protocol, and Internet World Wide Web protocol was developed. And in 1998, Google was born. And in 2010, this last decade was for the big data or the AI. So from then, the question was, what next? So around the 2002 to 2007, like parallelly, there was a development for the quantum related activities. So first development was related to how can we secure our data. So classically, if you look at the encryption algorithms, so they uses mostly the mathematical based approach, prime number factorization. So there still if you have the seed to encrypt the data, so how do you share these seed among these remote parties was still a question that has not been answered, or can we share it secretly? So this question was answered with the development of quantum key distribution. So there the idea is to share or generate the symmetric key, the same key among two remote parties. So this small network was developed in the US, and after this QKD demonstration, then private industry received very good amount of funding to develop quantum processors, etc. Right? So many of you might have heard about the Google, this Google processor. Even Willow came into the picture this year itself, right? This year or end of the last year. So IBM has something around 433 quantum bit, similar to the normal bit, so processor. So okay, after, let's say, we will have quantum, computer. Today you can buy a few qubit quantum computer, especially in the Europe and the US. So the question is, can we interconnect these devices, quantum computers, for example? So what we will need a network, and interconnected network, that is nothing but the internet. So the next decade or so will be the decade for the quantum internet. That's what I'm going to talk about in the remaining set of slides. So coming back a bit, you might have heard about these two quotations. So one by Albert Einstein, he said, the most incomprehensible thing about the world is that it's comprehensible, right? So the simple thing that we think is the most difficult things, actually. And another quotation is given by the Feynman. So he said, if you think you understand quantum mechanics, you don't understand quantum mechanics. So during his time, or even now, some of the postulates that has been kind of adapted for the quantum mechanics is still being debated. So in 1900, around 10s or 11, 1911, in the Copenhagen summit, they formulated postulates of quantum mechanics, and which has been kind of debated still. Why? Maybe we can see in some of these slides. But still, I mean, it's not like we completely do not understand quantum mechanics, or because you see, some of the gentlemen have already won the Nobel Prize for developing quantum, related experiments. For example, Alan Aspect at EPFL Zurich, so he developed experimental setups for generating the integral photons. And Clauser was awarded Nobel Prize for establishing the violation of Bell inequalities. Zeilinger, he's a pioneer in quantum information science, and most of us today actually read his book. Nielsen, no, not his book, but he has some good set of kind of teaching notes. But Nielsen and Chong book actually in quantum information science. So apart from these three scientists, there have been like many scientists around the world who are working and making the quantum mechanics, understandable, and developing the quantum related experiments. Okay, so yeah, so if you have questions anytime, please ask me. So yeah, so what is the difference between the classical versus the quantum communication? This question, I mean, this might come to your mind as it comes to me. So in classical system, what is the fundamental unit of an information is the binary digit. In short, we call it a bit, right? So bit is binary digit, so it's a 1 and 0. So typically we represent an on state as 1 and off state as 0. Or we can say if capacitor is charged, fully charged, we say 1, and if it is discharged, we say 0. And here we say that classical system must be in a state 1 or state 0. So remember, focus on this word or, right? It must be either this or this. On the other hand, in quantum system, we have a similar thing compared to bit. It's a quantum bit, right? So what is a quantum bit? I can give you a couple of examples. For first is the related to atom we can take. If an atom is in ground state, we say this, it's a qubit 0. We represent it with a ket notation. Okay, this is just for the sake of notation, so don't worry about these notations. And if it is in excited state, then we will call it qubit state 1. If we take another example of photon example, then we can say that if a photon is vertically polarized, we will call it it is in a state 0. And if it is horizontally polarized, then it's a state 1. We can also write these states in terms of like column vectors. So for example, horizontally polarized photon as state 0. So yeah, just I said the reverse, doesn't matter, it's just the relative thing. So here horizontally polarized photons, so you can write a column vector of 1, 0, and vertically polarized quantum bit state 1 is just the 0, 1, right? So the difference is here. Unlike a bit, which can be in either state 1 or state 0, here the system can be in superposition state, which is proposed by Heisenberg and which is still being debated. So meaning that a quantum state psi can be written as a superposed state of 0 and 1 with some coefficients. And here we have coefficients alpha and beta. But this also represents as a probability in terms of mod alpha squared and mod beta squared, and their sum must be equal to 1, right? So Heisenberg, so he introduced these things. So superposition actually phenomena. He thought that let's consider a closed system in which there is a cat. We don't know whether it's dead or alive. So until we open this system and see it, then only we can, until we do that, we will say that the state is in superposed state. And he wrote many letters to Einstein, which Einstein actually kind of, so he disagreed with, and I will tell a story in a bit, because I need to introduce one more kind of quite, one more important property related to quantum, which you cannot find in a classical system. So let's consider that now these 4 bits that a sender called Alice has, and she wants to transmit to a receiver called Bob, right? So Alice can transmit these bits error-free as long as the bit rate or data rate is below the channel capacity, right? That comes from the Shannon capacity theorem, right? In quantum, we have the similar thing. We have quantum bit, right? Quantum state we want to transmit from Alice to Bob, right? And the Bob must receive the same state, right? Which is actually, how do we do that first, right? So this is a very challenging task. Why, it will be clear soon. And so yeah, that's the question that people are still trying to answer. And why is it's a problem? Because it has a conflict with the quantum mechanics. Quantum mechanics actually makes it difficult. First thing is the no cloning theorem, which says that it is impossible to duplicate an unknown and arbitrary quantum state. So you cannot copy an unknown and arbitrary quantum state. If you have any node which you don't know how it was generated, you cannot copy it and transmit, which is very easy in the classical computer. And the second is the Heisenberg uncertainty principle. This comes from the superposition thing, that it's impossible to know a quantum state, right? Because it's superposed state, can be a superposed state. So superposition, you can think as a, the simple, like, let's say this string of bits is simply the summation of different states with scaled by some probability. Unless you measure it, you don't know which state it goes. And that also introduces a term called collapse. So after measurement, you will know the state, right? Particles can exist in multiple states at the same time, known as superposition, right? Superposition leads to uncertainty, right? So now another very important property of quantum mechanics is the entanglement, right? So before entanglement, let's revisit the statistical dependent, like when we say that two classical systems can be statistically dependent. So if it follows the following condition, right? So probability that bit 1 and bit 2, probability of occurrence of this joint probability is not equal to the factor of individual probability, right? Probability of bit 1 and times the probability of bit 2, like PAB. Okay, I don't need to write, but let's say PAB is not equal to PA times B, right? So we will say that two quantum systems or states can be entangled if they cannot be, their joint distribution cannot be factorized. For example, this is a famous state where we have, so entanglement is always between two or more particles. So for example, we have two qubit state system. So first qubit can be in state 0. At the same time, this second qubit is in state 1. Or so here it can be plus or minus superposition. Or the qubit 1 is in state 1. Same time, qubit 2 is in state 0, right? And root 2 comes due to the normalization process. So that probability becomes 1. Okay, so this is the famous Bell state. So Bell state, I will tell you later what it is. So entanglement, as I told you, it's a kind of a strange correlation. So you cannot describe an entangled state by simply knowing the individual states, right? If you want to describe the whole state, you have to describe that whole state. You cannot describe through the individual states, right? That's the complexity. So, for example, I mean, one you can see. So both are the superposition and the entangled at the same time. So here, if I give you another example, how can you kind of visualize an entanglement between two particles? Let's say we have an atom and we have photons. If an atom is in cold state or ground state, it emits, let's say, it's a hypothetical case, it emits a photon in the left channel. And or if this atom is in hot state or excited state, it emits a photon in the right channel, right? This is our state, right? Superposed state. So what is entanglement? So entanglement comes from that. Suppose we have two detectors here and here, right? So if we measure that a photon is received in the left channel, right? It can be received at the same time, either at left channel or the right channel, right? Because of the state we have defined. So if you receive or there is a click in the detector in the left side, we will know that without measuring the atom, we will know that the atom must be in the ground state or cold state. If you detect in the right channel, we immediately know that atom must be in the hot state, right? So that's the entanglement, right? If two particles are entangled, if you measure one, you immediately know the state of the others. That's what Einstein debated, that it is not possible that information can flow with more than the speed of the light, or in here, ideally, in this case, 0 time, right? And until the Bell came, and Bell proposed some of 4 states actually, this 1, 0, 0, and all different combinations of this. So you will have the 4 states in one of the slides I have. And then he proposed a criteria criteria which is called Bell violation criteria. And if you prepare any system or call it that it's entangled, it generates the entangled particles or photons. And if that follows that criteria, then you will say that it's really entangled, right? And typically the correlation has to be between 2 and between 2 and 2 root 2. Okay, so now moving to the quantum internet. Drink it. So basically, quantum internet, as I said, nothing but the interconnected networks. Okay, interconnected networks of quantum devices. So basically, quantum physics is transforming the information processing in computing, communication, security, and sensing, right? So we have several applications of quantum mechanics, and right, and also we will have the devices corresponding to those applications. So the idea is, how can we interconnect those devices and the applications? We can do that with the quantum networks, right? Or quantum internet, right? So this industry, those who are developing the quantum devices, they are getting the huge amount of funding, right? In the last, let's say, few years, for example, the Psi Quantum in the US, they have received billions of dollars of funding to develop the quantum computers. In the US, most of the focuses, today, lie in developing the quantum computers with the different, the different technologies, superconducting qubits or photonics based qubits or something. There are different the options for to have the quantum computers, but they are also like over promising, right? They want money. Of course, everyone wants money to work on, and they are getting funding, and they are promising a lot. We don't know whether the quantum computer, when I say quantum computer, that a computer which can do the meaningful work, right? Getting a few bits of quantum computer will not help. And to break an RSA encryption in a day or two, you need millions of qubits. And today, IBM has a few hundreds of, let's say, qubit. That's just for some task you can do, but there is no meaningful operation you can do, right? So yeah, we will see how it goes. We have two typical kind of applications: quantum computing and quantum network and security. So quantum computing can be used to break the the encryption algorithms. That's what it has promised, and that's why China, US, Europe, India, they are trying to kind of develop the system, so that, and everyone is fearing that if quantum computers come, then all the classical encryption, they may be able to break it, and all the data that we have over the classical internet or in the classical computers, that can be compromised. So there is another thing with the quantum machine learning, and we can use also it in the chemistry and materials. So these are still kind of in fancy, and we don't know whether it will fly or not. And in quantum networking and security, of course, this quantum mechanics promises the secure communication. Why? We will see soon. And also, quantum has the capability to have enhanced sensing, because unlike the classical, let's say the sensing here, only few particles, if something get perturbed, few particles will be able to kind of sense it and perform the job. But at the same time, it's also challenging. Okay, so now let's go to the next topic. That's actually the quantum internet, and I gave you some idea, but let's formally define it and what are different challenges, right? What is quantum? What is the internet, right? So internet, as I said, is a global network of networks to transfer bits of information, right? So throughout, let's say we are living on Earth, and we are all connected through the devices, and devices are connected over the internet, right? So, but if you divide this internet, then we have the access network, where local area network, so where these buildings and individual, let's say the nodes or computers are connected, and then we have metropolitan area network. And finally, we have the interconnecting those metropolitan area network by the wide area network, right? Similar to that, we will have to build the quantum internet, right? So quantum internet, so unlike this classical internet, what it will do the same thing, but it will transmit or transfer the quantum bits of information, right? That is what we have to build it for, right? And it uses the same and optical medium. Typically, these in the the wide area network or the metropolitan area network or even the access network. Typically, we use the fiber. We also use limited, or complex terrain, the free space, and other things. But typically, fiber we use, and the wireless, of course. So idea here is, what I'm saying is that we have, like the question is, how can we use the existing infrastructure to develop the quantum internet, right? So that's the idea. Unlike, we don't want to kind of completely overhaul the existing infrastructure and develop a new kind of infrastructure for the quantum internet, because that's not feasible, right? So yeah, how can we do that? I mean, these questions are still unanswered, and we need to find the solution. In classical networks, so as I was saying, that we have the access network, we have the metropolitan area network, typically in a ring, connected in a ring fashion. And then we have also these continents connected over the submarine fiber cables, right? We have third options of going through the satellite laser communication, which can interconnect people and the nodes, right? So if you look at the classical, let's say, how do we transfer the bits of information in the classical network, right? So let's say, even though we want to transmit one single bit of information, right, depending on the data rate, how many number of photons does it need, right? That question you can answer easily. So let's say you have one photon, energy of the one photon is simply h nu. H is the Planck's constant, and nu is the frequency, right, of the photon, right? So you can compute its energy, and depending on how much energy joules you are putting it in transmitting one bit, depending on the bit duration or the data rate, you can compute how much energy it takes. So you can divide it with the single photon energy to get the total number of photons per bit, right? So it will be typically in thousands of photons you will have, right? You will need to transmit single bits of information. Unlike that, in quantum information science, we can use the single particle or single photon to transmit a single bit, right? So that's the quantum. Okay, but there is, as I said, there is an, or I might not have said, there is a no cloning theorem from the quantum. Oh, I mentioned this, I remember now. So no cloning theorem, as I had introduced, it simply says that we cannot copy an arbitrary unknown quantum state. But you remember that this is the reason for enabling the security, right? And third party cannot simply intercept and copy it, right? So that enables the security together with the superposition state that brings them uncertainty, right? So how do we actually transport the quantum state from one place to another place? That's the key challenge that people are trying to address. And in quantum domain, we call it a teleportation, right? So how can you transmit uh, quantum state from one node to another node, right? So we will look at this in brief. Another thing that you need to kind of understand is that how do we amplify the classical, let's say classical bit, right? After, let's say, yes, when a signal propagates, then it gets attenuated over the medium, and then a receiver receives, right? If the distance is long, then you need to use the amplification, and not only amplification, you also have to regenerate and retime, etc. We might need the repeater depending on the distance and all, right, and the loss. So how a classical signal is amplified. So in let's say the fiber optics, if you send the information through photons, because of the loss, let's say 3 dB loss, if it has, typically one fiber has 0.2 dB per kilometer. So so after, let's say, typically 80 kilometer, you need to have such amplifiers. And and it also depends on the receiver sensitivity. Okay, so their amplification is simply adding for the same bit, let's say 1000 photon you send, and after 3 dB loss, you receive 500 photons, right? So you need to put the another 500 photons there, right? That's amplification process with the same frequency and the such that they are coherent. So amplify you can do in amplification, you can do in classical, let's say, network. But how can you do in quantum network? So you cannot do in the quantum network. That's the key, one of the key bottlenecks in the for developing the quantum internet, right? The signal cannot be amplified, right? Okay, why do we need quantum internet? So, I mean, today's internet, that's typically based on the transport control protocol or internet protocol. In short, we say TCP/IP provides the best effort services, meaning that it doesn't tell us that how many milliseconds your data will be delivered and so on. It will not guarantee that. It will just tell that it will try its best, right? Depending on the congestion, like how many, how much the links are loaded and so on. Your data will be delivered if you use the TCP IP, right? The scalability is another problem. Data security is a big problem in classical network. And if you calculate energy per bit or information rate per photon, that's actually the key challenge in the classical network compared to the quantum network, right? And slow data processing is another, like one of the key challenge in the traditional classical internet, right? So on the other hand, if you look at the quantum internet, as I said, it's governed by two key properties called superposition and entanglement. So we can utilize these features and develop the quantum internet, right? So it enables the unconditional security, meaning that you can prove the theoretical information theoretical security, and also it provides us the opportunity for energy efficient design. And the key thing comes from here. So exponential speed up in processing n qubit. I'm not sure. Let me see if I can write or something. Okay, I don't see the pen here, so it's okay. So n qubit can annotate. Okay, I'm not seeing here. So what is it? No. Okay, so n qubit can process 2 to the power n functions at the same time, right? Which is not possible in the classical classical computer, right? So it's exponential speed up. So what we need in order to develop the quantum internet, we need to build quantum local area networks, metropolitan area networks, wide area networks, right? So these things we need to develop it. How can we do that? I mean, there are several proposals, and yeah, so in order to develop the quantum internet, as I said, we have to work and develop many quantum devices, from edge nodes to the router to repeaters. So basically, repeater is nothing but the advanced repeaters or the third generation repeaters will have the 3R functionalities. So 1R is regeneration, retiming, and reamplification, right? So that you can send information from one continent to another continent by using interconnecting these repeaters over some lengths, right? So these and also we can use the satellite quantum communication, which China has already demonstrated, and that's why these some of these countries, including India, have woken up and started funding. So in Chicago, there is already work going on. So they have around 200 kilometers of network, and recently, actually, Northwestern University have demonstrated just in December this year quantum teleportation over, but it's not over 200 kilometers, just around small length, 30 kilometers, I guess, and but this network is located around 200 kilometers. And China, if you look at on the other hand, on the right side, so they have developed or deployed 4,600, or in fact, this is the kind of couple of months old slide, so might be 5,000 plus kilometers, right? So but what is the okay, don't get by seeing this data, I mean the numbers, don't get like overexcited. So what it simply says that they have intermediate nodes, which they call that they are trusted, meaning that they have to kind of get the data, decode, encode, and then again send. So it's not end to end kind of, right? So, but still, it's a like huge, like big, huge work, right? So China is leading, and US also. There is there are some work, I mean, going on. But the US focus is towards the quantum computers, which China might have, but they are not revealing. But what they have revealed is the quantum key distribution network, and also based on the satellite in around 2010s or something, they have already demonstrated how can we distribute the quantum keys between two remote from Beijing and another city, and also they have done with the one location in China and in Austria, which when Indian Prime Minister went to Austria last year, so he met Zeilinger, and he pushed the National Quantum Mission, and yeah, some of us, we got the funding, from the National Quantum Mission to develop these quantum networks, or other related things. So let me drink a bit. So I see something in chat. So how can this be achieved in a realistic way? I'm not sure. So on which slide it is? Maybe you can ask me at the end, because I'm not sure which maybe sorry, yeah, which slide you are referring to. So yeah.
Yeah, this is posted by I think some of the participants.
Yes. Yes.
Dr. Magarajan. So can you just brief your question, sir?
Yeah, or the slide number so that I can go.
Yes. Can you post the message once again clearly? Sir, I think you can move on to the next topic. Meanwhile, when he posts,
Yeah,
we can
yeah,
come back.
that's right.
Thank you, sir.
So, okay. So what are the works that have been done in India? Let's see that, right? So ISRO has been working, ISRO, so has been working in this quantum key distribution area for few years, and in Space Application Center in Ahmedabad. So they have demonstrated free space quantum key distribution between two buildings, and there has been some work also in Hyderabad, and also ISRO is trying to do it satellite based, which I'm not sure when they will be able to demonstrate it, but maybe within few years, because they have given projects to some partners. So in this SAC Ahmedabad center, they used one of the key QKD quantum key distribution protocols named as BBM92. This is entanglement based protocol, and they have demonstrated over 300 meters in our free space, because free space is lossy, so distance is an issue there. But if you use the fiber based, yeah, it can be done. Okay.
Sir, there is a question from one of the participants. Can now any quantum technology in wireless or mobile ad hoc network?
Yeah, that's a very good question. Though wireless, when you say, okay, so free space, if you don't consider free space optics, as a kind of typical wireless domain at operating at, let's say, the few gigahertz or terahertz and lower terahertz regime, then there is a problem. So if you have lower frequency, that's why you see the typical quantum communication applications or quantum computing, the frequency is in higher end of the terahertz, right? So there, the noise number of dark, the let's say if you want to generate a single microwave photons, along with that, you will have so many actually number of photons generated to that. There is a formula, square root of n. So and there is a frequency relation. So lower end of frequency, we have so many noisy photons generated. That's a typically big problem at typical wireless network. But if we can overcome that, then you can have at lower end of typical wireless, let's say the wireless or microwave photonic range, right? So that then we can have quantum communication in that range also. But today's typically it happens in the terahertz, right? So over free space or 1380 nanometer or 1550 nanometer, around this range. So we have the source, we have available in the market, detector, etc. And for lower frequency, one still has to overcome the noise problem. Yeah, I hope it answered your question. So let's okay. So next, why it's not sure. So this is okay now. So there is another work coming up for developing the quantum network between Roorkee, my institute to IIT Delhi. So over the 6-node network, and you see between some of these nodes, there will be entanglement-based quantum key distribution protocol that we will implement, and over larger distance, we will be using possibly there are actually two variants of quantum key distribution protocols. One is called CV based, meaning that continuous variable, and another is discrete variable. So continuous variable means that we can use the continuous property of light, such as amplitude, phase, etc., and modify that, right? Something, you can use that property to have this quantum key distribution. On the other hand, dB means discrete variable, meaning that discrete state of lights, such as polarized or some other, parameters. So typically it's the polarization. So we horizontally polarized, vertical polarization, etc. So these are discrete, variable. So discrete has its own advantage over continuous, but for continuous variable quantum key distribution, we can such as one of these protocols, we can use the classical actually optical devices. So it will provide us the cheaper solution. On the other hand, for entangle based protocol, we will need the single photon detector, etc. And if you try to get a superconducting, that's the advanced one, superconducting nanowide single photon detector, then it's a very costly, right? So each node has huge, I mean, the cost associated with. So, okay, so we also have, apart from these are fiber links, what you see in the black, and we also have the free space link, right? So we will also try to demonstrate some CVQKD over the free space link, as well as entanglement based protocol, QKD protocol over this free space link. Okay, I don't have the slide for another work that has been funded. Before that, this work has been funded by the National Quantum Mission last year. Similar, I mean, not similar, but there is another network coming up from Chennai to Bangalore, IC Bangalore, from IT Madras to IC Bangalore. So where the focus will be on CVQKD, because the distance, if you maybe you can tell, so few hundred kilometers. So longer distance, it's hard to use the entanglement based protocols, because of the single photon lossy and all loss, etc., associated with that. Unlike here, where you can use the classical transmission. So yes, so another work, so two parallel works will be done over the period of 6 to 7 years in India. ISRO has also allocated one project, and with satellite based, we will see how they, how they progress and so on. Okay, so there is some promise, and of course there are some challenges, but there are opportunities as well, right? So we can use the quantum properties to build devices, develop algorithms and protocols, and we have like everything. Nothing is done actually. You can say that. So we have to develop quantum processor, quantum memory, etc. We have to develop quantum protocols, algorithm simulation models, etc. We have to solve the quantum entanglement distribution problem. We have to come up with the innovative solution for teleportation problem, which I am going to describe a bit. And the main problem remains is the quantum error correction. So similar to the classical error correction, when we transmit the data at the receiver, some bits go in error, right? So then we use the error correction methods to correct it, right? So here the challenge is in quantum domain, how can we, do the quantum error correction? So recently I heard one talk from this Psi Quantum CTO, Mark Thompson, which the company I mentioned is leading in the US to develop, have been assigned the task to develop the quantum computers. So he was saying the scalability. Today you can have few qubits, but if you want to solve the real problem, you need to have millions of qubits. And so meaning that we need to solve the scalability problem. And the currently problem lies in the quantum error correction. We don't have such techniques. So yeah, these are some of the open fields, open problems that one has to solve to get, the quantum, computers and quantum internet, in the future. Yeah, so everything needs to be done with respect to, quantum processor, memory, etc. Why it's a big problem? Because, as these entangled photons or the single particles, as they travel, the pair of particles, they lose the coherence property, meaning that if the phase difference, changes over time, right, between two particles. So coherence, or in quantum term, we call it they decohere. And synchronization would be another issue that one needs to solve in a network. And so quantum hardware require high speed, low loss switches. We need to develop the repeaters. Repeaters have not been developed in quantum domain yet. There have been theoretical proposals, but no practical repeaters are available that you can buy from the market yet. So we need improved sources, like the rate is the big issue. Currently, we can have few kilobit per second, photon generation, and detectors currently yeah, it's very costly, and also efficiency. If you have SN, this superconducting based detector, it can have efficiency up to 99%, but it's very costly. So it uses the cryogenic system, which means that it has to be cooled to up to around 0 Kelvin to keep the noisy photons or the dark count very low. Okay, so room temperature based, we need detectors which works at the room temperature. We do have such detectors like avalanche photodiode based detector, but efficiency there is only roughly like 20-30%, which is not good, right? So out of 100 photons, 30 photons will be lost at the receiver itself due to its incapability. So yes, everything needs to be developed, right? Yes, I see another chat. Okay, I see you are asking the question. So Somadeep is asking, in India, where is the better work, or specify the name of scientist in India about quantum internet? It's nothing like better work or bad work. It's in India, this work has been just started. So if I name from IIT Delhi, there is a past Professor Bhaskar Kanseri group, and here at IIT Roorkee, I'm doing with Professor Anshul Jaiswal, and IIT Madras. Sorry, Professor Anil Prabhakar's group is doing quite a bit nice work. So they will be. He's the lead PI that will develop. Sorry, that will develop the network from Chennai to Bangalore. So yeah, so there have been, okay, so PPT and content link. Okay, good. So I can share. I have already shared the PPT, in the PDF format. So maybe host can share with you all. So no problem. Yes. So yeah, so there have been also, so it's not about only the network. We need to work on several aspects, as I was mentioning, right? Software, hardware, everything. So now coming to the quantum internet a bit in depth. How much time do I have? Okay, 7. So classical, if you look at the classical computer network, right? It is governed by so-called Open System Interconnect, OSI model, or this has been modified with the TCP/IP stack, which has only 4 layers, in which application, presentation, and session has been merged into just application. And then we have transport layer, network layer, and these two, data link and physical, is also merged into Ethernet layer. So basically 4 main layers we have, or we can also call it 5 layers. So each layer has its own specific task. So physical layer, for example, how do we represent the bit? How do we put the bit on the wire? That will be the link layer. How do we switch route, etc., from source to destination? That will be the job of network layer, meaning how do we forward data or in the form of packets or whatever, and how do we take it, switch it to the destination, and so on. Route it from source to destination, right? Transport layer. So how can we reliably send the data from source to destination? And application layer. So what kind of applications you want to run on the network, right? So we need to develop for a particular application. We need to have a application layer, right? So similar to that, in the classical network, we have to develop the quantum, protocol stack, right? So here also, how do we generate the quantum bits, right? How do we transduce these quantum bits over a link, right? How do we switch route these quantum bits over a network, right? How do we, transport end to end, route from end to end over over the network, right? So reliably also. So that's the transport layer. And applications similar to quantum key distribution is one of the applications, right? That one can use, to run on the quantum network, right? There are several applications, right? So yeah, you can refer to this detailed survey paper for detailed description of all this. And okay, yeah. So if you talk about the physical layer, so basically, as I mentioned briefly, so what we need quantum devices to generate or receive qubits, right? We need quantum memory to store qubits. We need quantum, let's say, fiber or free space as a propagation medium, right? These are the physical layers aspect. When it comes to link layer, then it will be how do we generate the entangled photon? How do you transduce these entangled photon or bits, to the on the wire or on the quantum links? And also it has to perform the error correction. So quantum error correction, how do we do that? So these things one needs to solve, right? Or the task of this network stack is like that. Okay, so how do we generate entangled photons? So there are two types of qubits that can exist in a quantum dot. One we call communication qubits, which is used for generating entangled states, and there is a memory qubits, right? So it's used for storing the quantum states. If you have stored some, like typically we have in the hard disk, the bits. So how do we, you copy it, click it, copy it, and then you also send it, right? For example, email and so on, right? So those applications, how can we do that? So we need the qubits in memory as well as qubits for the communication, right? So these qubits are typically known as the matter qubits, and there is a meet in the middle protocol. Just a minute, sorry. Okay, so let me put it down. Okay, so yeah, so here what this is, how do we let's say the transfer the one and how do we entangle, how do we transfer the entangled sorry, entanglement state, right? So this is one of the protocol meet in the middle, and here what you see in the brown circle we have communication qubit. In the yellow circle we have photons which will basically carry this information, and we have in the blue circle we have memory qubits in which the actual qubits are stored. And here we want to basically through the photon emission we want to transmit these bits, right? So this what this protocol says is that each node first prepares an entangled state between its own communication qubit and a photon, right? What you see, this is once you have the entangled state, you basically make these two photons or state entangled, right? After that, the two nodes emit the photons simultaneously from the node 1 and node 2, and they meet in the middle, right here, as you see in this picture, right? And they perform the so-called Bell state measurements, like a projection or the measurement basically that which quantify if they are entangled or not, right? And the results they communicate over the classical channel. Okay, so for Bell state measurements you can use the linear optics, single photon detectors, etc. And typically success probability is 50%. Both detector has to be clicked at the same time, right? So coming from this one and this one, right? So which is a bit challenge. And if BSM is successful, that indicates the communication qubits at the two nodes have already formed the entangled state. Then we say that they are entangled, and then you finally the state can be transferred from the communication qubits to the memory qubits for better storage. We will say that these two memory qubits have been entangled. Okay, so there is another scheme for entangling the memory qubits, and it's called sender receiver scheme. In the previous scheme what you saw was this measurement or so-called Bell state measurement was in the middle. That's why the name meet in the middle. Here we do the Bell state measurement at one of these two. Here it's shown as at the receiver. All the steps are more or less the same. Okay, and after this, if this measurement is successful, then you do the similar operation. Another scheme is called a midpoint source. Here, instead of having the the transmitting the having the source here and here, so you have a single source which generates a pair of entangled photons, and then you transmit and perform the Bell state this measurement at the both nodes, and then finally you entangle these memory qubits, right? Okay, and that's important. Why? Because we want to transmit the quantum state from this node to this node, right? So yeah. Now coming to the network layer, basically there are the question that you will be answering, how can Alice transmit, let's say the sender transmit the state, let's say psi to Bob, receiver Bob, right, far away, right? So you need to, and there are two typical, the operation that one needs to kind of follow. One is called entanglement swapping and quantum teleportation. Okay, so yeah, so these two things are quantum. I see some questions. Quantum networks operate fundamentally different from classical networks. Yes. To transition from classical to quantum supported device, the entire computing infrastructure must involve. Here is how what we can achieve successful quantum-based network communication. Yes, you are right. So complete, I mean, I'm not saying that we need to kind of overhaul the complete infrastructure, but yes, supporting, let's say the whatever needed needs to be kind of developed, but we can also reuse some of the infrastructure. For example, we have typical example, low loss fiber, low loss switches, etc. Right? So some of these things we can reuse from the classical, right? Only thing is that the nodes you need to, have source detector, etc. And yeah, I think that's all. Okay, so just I will kind of go briefly because this is not, I mean, so easy in few minutes. So how to do entanglement swapping? As the name the swapping concern. So basically, let's say A and B are entangled, right? These two. Then and also C and D are entangled, right? So basically, we want to swap the information from here to here, right? So we want to entangle these two, right? These two nodes. How can we do that, right? So again, we perform the Bell state measurement. If these two nodes can be entangled, we will say that these two nodes are also entangled. Then the A and D will be entangled. And you have to do for Bell state measurements. You need to project on the Bell basis. These are the 4 different states I was kind of mentioning in some of the slides before in the beginning, right? So all these combinations 0, 0, plus 1, 1, 0, 0, minus 1, 1, or 0, 1, plus 1, 0, 0, 1, minus 1, 0. These are the 4 states that Bell sorry, came up with, and until 70s, people believed the Einstein theory that there is some hidden variable or hidden theory that we don't understand in the quantum, and that's why it violates the Einstein theory of relativity. So Bell proposed this 4 state and said, if take this example of 4 states, and this we will call it maximally entangled. Okay, the correlation if you perform, you will get 2 root 2. So here is that if you can generate a source which is able to generate in any of these 4 states, then you will have the maximum entangled state generating, right? Which is typically not possible, but yes, we try to achieve that, right? This maximum entangled state generation and also the reception then, right? So now coming to the quantum teleportation. So basically, how can we teleport a quantum state, let's say psi, from node A to B? Once they are entangled, then that's the idea, right? So we can do this kind of theoretically, I mean, easily. So we perform the Bell state measurement at node A, and once you perform this, you will have some, let's say, 2 bits of classical information and which you can communicate. And at node B, you need to perform some again mathematical operation, and you can basically, without transmitting the actual state psi, which is not possible, right? As in, due to no cloning theorem, you will be able to regenerate this quantum state psi. That's the kind of proposed by Bennett. And this is the original author from the BB84 quantum key distribution protocol, Bennett and Bassard, right? So he also proposed the first teleporting theoretical, conceptual protocol. Right. So although, yeah, people are trying to realize it, but yeah, due to the many different challenges, it's still not there. I mean, it's there, but trying. I mean, on chip, and there are other things. There are still many problems that are kind of hindering the development. So quantum repeaters, as I said, repeater means The third generation repeater means it will do the 3R operation: regeneration, retiming, reamplification, to take any data from one node to far to far away distance, right? We need to use the repeaters, right? So we need to develop quantum repeaters, which does not exist. But yes, there are again theoretical concepts, theoretical protocols for this, but people are trying. But we don't know whether it will come or not, or when it will come, right? So there are different, generation of repeaters, which theoretically people have already proposed, although not even this first generation repeater that came into the market. And depending on whether they are able to perform error correction and all, so the three different generation of repeaters will have different personalities. Now coming to the transport layer protocols, similar to the classical transport layer protocols, we need to answer some of these questions. For example, what kind of congestion control we will have in quantum network, right? Congestion means that when you have, let's say, many data packets coming into the network, then at the switch or so, they get buffered, right? So there is a congestion on the link, there is congestion on the devices, right? So how can we develop the congestion control protocol similar to the classical network, right? TCP. So, and also in classical, if you don't receive the data packet correctly, then we need to do retransmission, right? TCP does that. Here, how does this retransmission will work? Yeah, these questions are still unanswered, and one needs to work on. Okay, so what are different another, I already mentioned you many challenges, but let's look at some more challenges. Let me drink a bit of water. Okay. So this is from my former advisor at UC Davis. So how do you achieve transport in quantum networks without destroying qubits? Yeah, this is the fundamental question that one needs to answer if you want to develop a quantum network, right? Why? Because the problem is you cannot copy, right? And once you measure it, it's gone, right? You cannot regenerate it, right? So how can you do that? I mean, this is the big problem. How do you switch and route the quantum packets in quantum networks without destroying them, right? How do you place a control plane? Control plane meaning that which will inform the switches and routers how to switch and route, forward and route the data. And how do you manage this? Management plane comes into picture. How do you monitor the performance of quantum networks? Do we have, the devices and test beds to develop the quantum networks? These are some of the questions that one needs to answer, right? And if we do have such devices, then are we going to, overhauling our existing network? The answer is of course no, right? So we cannot dismantle the classical network and completely replace with the quantum, right? And yeah, so the idea is, so can the classical and the quantum network can coexist or not, right? So of course it has to coexist to bring the cost down, and also use the backward compatibility, right, with the today's network, right, and to develop the future quantum internet, right? So some of these questions have been answered with my past work and also with the current work. Yeah, so I will kind of briefly go over them because we have limited time, or I'm not sure. So will are the participants able to unmute and ask questions, or they will type only?
They will type only.
Okay, fine. So yes, so you have only less than, I think, 14 minutes. So please feel free to ask questions. So here we worked on quantum wrapper networking in order to answer some of these questions. Here the idea is that, let's say you want to transmit a data from one node to another node, right? One network to another network, and how can we do that, right? So typically the problem I told you, the no cloning, you cannot copy, you don't know how to switch and route and so on, right? So if you process the data at the quantum data at the intermediate node, you cannot regenerate it, right? It's gone, right? So what Professor Prem Kumar and Professor Ben you proposed was, let's have a data grammar packet which is similar to the classical, where the header. Okay, I will explain that. Header is in classical bits, classical domain, and the payload where our information is there. So that's in quantum, the quantum bits. Those are the quantum bits, and again the tail is there. So header basically and tail, they allow us to know what is the source IP, destination, other addresses, etc. That helps the data packet to take from the source to destination, right? How it will know that this has to go through this port or this port. So, these things are, solved by the header, right? So this we keep in the classical domain, classical bits, meaning that one bit is in this here, one bit will be represented by thousands of photons classical, bit we will have. But here we will have single photons, entangled photons here. So by this multiplexing, we can, solve this problem somewhat. Okay, and this header, typically you have some of the information which classically we have, preamble, etc., error correction, etc. So we need to also develop the quantum wrapper switch router. So basically, if you look at the switch, what it will do. So you have header, payload, and tail is optional. So when it arrives at any switch, let's say 1/2, it gets it. So basically, we will demultiplex it by timing, timing information, and header will go through some processing, and the quantum data, header is in classical, right? So quantum data will go through, just delay line. So once it's processed, right, you will generate a new header kind of thing, and also you will be able to switch which port it can go, right? By the time you align, or you link those ports, right? So it will be again multiplexed and switched to a right destination port, right? So this can be done. And we also performed some point-to-point entangled photon distribution, yeah. And yeah, so as it was started from the source, then it went over to, few hundred, not few hundred, few kilometers of fiber, and then at the receiver we kind of demultiplexed and performed some measurements. So some of the experiments we did, and we also had some results related to the what is the the quantum header bit error rate versus the attenuation. Attenuation is basically like if we are using different length of fibers, right? So based on the loss, how much, how the bit error rate of the classical header header bits, so typically if you have increasing in attenuation, obviously the bit error rate will increase, right? And similar to the quantum signal to noise ratio, we have the classical signal to the classical signal to noise ratio. We have coincidence to exponential ratio, which is nothing but the quantum signal to noise ratio. So basically, this also will affect, right? So increasing the classical, bit error rate will also degrade the quantum SNR, basically, right? And we also did some couple of experiments. If you transmit the classical and quantum over two different wavelengths simultaneously, your quantum coincidence count, meaning that two disentangled photons arriving at the same time, this has some certain, performance. And if you do in the multiplexed manner, then your performance improves. Coincidence, as you can see here, right, to 12.6 dB in the this mode, burst mode we call it, and here the 3.7 mode. And yeah, so future, I mean, we have to work on the switching, swapping, etc. And yeah, so just to kind of come to the end, more or less, I would like to announce that yes, at IIT we have a new MTech program, arts communication and sensing. And since I have joined here recently, so I have many PhD positions, and I have kind of couple of big funded projects. So yes, I have collaborators in Germany and USA. So yes, there is an opportunity for students to work, go and learn, because we have still I'm trying to develop the lab, but yeah, they have the much already developed lab. So yeah, I continuously kind of I'm collaborating with them, and I work on quantum communication and networks, data center, basically networking part, and also use these days AI ML, yeah, everyone uses for solving some problems, right? Students are also inclined towards that to get better job opportunities. So I do have internship options for bachelor, masters on these things. Yeah, you can encourage your students if they like to learn and do some work. They can approach me through email, and also I have listed some of the projects here. And I one more project apart from this National Quantum Mission project that I was showing you. So I have one US India funded project, the CV QKD seeded quantum noise stream cipher encryption. And yeah, so where I will be collaborating with Professor Prem Kumar. And here the idea is to develop quantum noise stream cipher, protocol. So yeah, this I was mentioning this project funded by the National Quantum Mission. It's a huge project, and yeah, we will be working over the period of 7 years. So this project also is very promising, challenging, but yeah, lots of things to do. And yeah, finally, I would like to acknowledge my, the advisors, former advisors, collaborators, etc., from Germany, US, and of course from India, Professor Krishna Sindham, and from IT Madras, and so on. So if you have questions, please feel free to ask me. I see some in the chat.
Sir, one of the participant raised the hand. I have tried unmuting. So, Somdeep Singha, sir, can you just ask your question?
Yes, yes, ma'am, I am audible.
Yes, you are audible. Please proceed.
Yes, sir, you say that Professor Prem Kumar, there was a channel, classical or quantum channel, where the quantum wrapper datagram flow. This channel was established in quantum channel or classical channel? Yes. Yeah.
Okay, so in this simple experiment, what we did, let me go back to, so here, so we are using the wavelength division multiplexed, channel. So classical goes over one channel, around 1590, around 1540 something, but the difference between these two channels were only 10 nanometer.
Yes.
And in one experiment, what we did, we continuously transmit the entangled photon data here, and also transmitted the classical with the PGA. We transmitted the classical data, calling it a header, right? So our different wavelengths in this, yes, we did, right? So both we call it, channel, if you say so, both are the same, right? But only thing is, how do you represent the bits, right?
Bits, okay.
Right,
okay.
so that's the key. But if you look at the next experiments here, okay, so one was the continuous, if you remember, and another was, okay, maybe here, right? And this was the continuous mode. You transmit classical and the quantum data over different close, wavelengths, continuously. And one was in the time division multiplex manner.
Multiplexer.
Yeah, so you see the performance, it improved a lot. And one can also do, this is like WDM TDM multiplex. One can only do over the TDM, but the problem at that time was, if we only do the TDM, meaning that same wavelength used for classical and quantum, we were fearing that the detector may burn if there is a leakage, if we were not able to control, from the classical bits, which has high power. So that's why we did like closed wavelengths, so that was there. And then we also worked on the preliminary work on, 3-node network, how to switch and route. Yeah, so I think that's the answer.
Okay, sir. Thank you, sir. Thank you.
Yeah, so uses of quantum sensors in quantum network in place of traditional sensors. So
anybody is having doubts, please press the raise hand option. I'll enable you to talk.
Okay, so I see one question actually. So what I'm adding here, what are the uses of quantum sensors in quantum networks instead of traditional sensors? Right. So I do not work in quantum sensing, but as you know that quantum sensor provide the enhanced sensing. So yes, one can use the quantum sensors in quantum networks, like distributed fiber sensors we use. So they are instead of like the continuous or the normal classical laser, you can use the classical not classical quantum source, but there you need to do interference, right? Interference, how to say, so yes, two particle like the typical example if you see is the this thing in the US where two arms to detect the, how do you say, these waves. So they are the nice examples. So yes, you can do the quantum sensing. Yeah. Liquid, how to say, the colline or not. If somebody can help me, this in US, India also has proposed for many years, but they haven't. India has not built it. Yeah. Over the not Magzender, this Michelson interferometer, right? So L shape. So where this, how is it? What is the name of the waves they have detected? Very famous experiment or the result. Okay, so yes, if there is yeah, no more questions, I think then.
Yes, sir, there are no more questions. Shall we go for the next session, sir, and shall we wind up?
Yeah, sure, sure.
Okay, sir. Well, thank you, sir. I
That's
just
much.
want to thank you. Um, um, I thank sir for your lecture session on quantum internet opportunities and challenges were very insightful and thought-provoking, and your deep dive into the potential of quantum communication, entanglement-based networks, and the challenges of scalability and security, which provided a comprehensive understanding of this field. The way you articulated the complex concept and clarity in real world implication was commendable. Your insights not only sparked curiosity but also emphasized the transformative impact of quantum technologies on the future of secure communication. Thank you, sir, for sharing your expertise and inspiring us to explore this fascinating domain further. Thank you so much, sir, for spending your time and accepting our invitation and sharing your expertise in this domain. Thank you so much, sir. Thank you.
Thank you, everyone. Thank you.
Thank you, sir.
Yeah. Bye bye.
Yes, sir. You can leave, sir. Thank you. Participants, you can take 10 minutes break, and after that, the next um, expert will join, and she will handle the next session. Feedback link will be shared at the end of session 2. Okay, so there is only one feedback link today that will be shared at the end of this session. Okay, not the session 1. After session 2 only, it will be shared. So you can take 10 minutes break and you can join. Thank you. Kindly stay back in this link. Ma'am, can you check your audio and video control and share option?
Yeah. Am I audible?
Yes, ma'am, you're audible. Good evening, ma'am.
Good evening. I am just sharing my screen. So if you...
Okay, ma'am. Now the audience gone for 5 minutes break, ma'am. After that, they'll join. So 7:35, 7:35 will start.
Okay. So my
Okay.
screen is visible.
Visible, ma'am. Visible.
Oh, why the security? Okay.
Yes, ma'am. Yes.
Yeah. And I'll just switch on my audio. Actually, it's very late. I am just 2 minutes. Just give me 2 minutes. I'll switch on my audio.
No problem, ma'am. No problem. Ma'am, we can able to see you. Mic muted. Mic.
Yeah, hi.
Mic.
Good to actually interact with you. So maybe while the others join, maybe I get to know about you and your university.
Yes, ma'am. Yes, ma'am. I am Dr.T.JEMIMA, Associate Professor in the Division of Artificial Intelligence and Machine Learning. And I'm here for 18 years.
Wow.
I hope you are in 21 years experience, right, ma'am? Right?
Yes.
21
Like
plus.
yeah, more than that. I joined this job in 2003 January, but I finished my PhD in 99. So we are of the same age. Maybe I'm much
Yes.
older than you, but yeah,
Yeah,
it's
little.
actually like,
When I
so
have gone through.
so you have undergraduate students, or you have both postgraduates and undergraduates with you?
Both. We have engineering. It's an engineering university. We have
Mm-hmm.
UG students as well as PG students, and PhD degrees also there in engineering, as well as arts and sciences also going on.
Okay, okay, that is good.
And
So,
MBA degree is also here.
okay. So, I mean, that is actually good to know, you know. I mean, if there is a way to collaborate, and I think we are always looking some students, you know, these days, getting PhD students and maybe motivated MTech students also is something very difficult. So, if you
Yes, ma'am.
think that there is a way that we can do it, that will be actually good.
Yes, ma'am. Some of our faculty members also attending this webinar, as well as some of the research scholars also from Karunya University, and they are also part of this FDP. They have also joined.
Okay, that is good. Actually, I've kept it very basic. So, I mean, because I mean, generally people from different background they do attend. So, I'm just trying to start from a very basic thing and building it. But definitely, if somebody is interested in working in this area or related area, we can define the problem and do something in that sense.
Okay, ma'am. Good to know all these. Okay, ma'am.
Yeah.
Shall we start the session,
Yes,
ma'am?
yes, yes, yes.
Good evening, all the participants. On behalf of Division of Artificial Intelligence and Machine Learning, Karunya Institute of Technology and Sciences, Coimbatore, I welcome all of you for the second session today. The resource person of this session is Dr. Monika Aggarwal from IIT Delhi. Ma'am is an associate professor at IIT Delhi, specializing in signal processing and communications, and she has completed, as ma'am has said, a PhD from IIT Delhi in 2000 and has been a faculty member since 2003. Her research encompasses areas such as sensor array processing and underwater acoustics. In addition to her role at IIT Delhi, Dr. Aggarwal is a co-founder of Krishi, a company focused on quantum computing to transform the finance industry. Dr. Aggarwal is also actively involved in professional organizations. She served as a chair of IEEE Signal Processing Society, SPS Delhi section chapter, and faculty in charge of IEEE student branches for SPS, Women in Engineering WE, Oceanic Engineering Society OES, and Marine Technology Society MTS at IIT Delhi. Her research interests are diverse, covering various signal types, including acoustic snow avalanche signals, biomedical acoustics, underwater acoustics, and multidimensional image signals. She is also engaged in classical problems related to direction of arrival estimation, beam forming, target detection in radar and sonar application. Currently, she is contributing to the design and development of underwater acoustic and light-based communication system and has a passion for quantum computation. Dr. Aggarwal has an extensive publication record reflecting her significant contributions in this field. Ma'am is going to discuss with you today on the topic quantum image processing. Welcome, ma'am. Now you can take over the session.
Thank you, Dr. Gemina. It was a nice introduction and very comprehensive. And thanks a lot. You have like I just see that you have almost 200 plus audience. It's actually very difficult to get such an audience these days in an online form.
Yes.
Thanks a lot for giving me this opportunity to present little of my work on this behalf of this audience. Uh, I hope my screen is visible.
Yes, ma'am. You
Yeah.
can proceed,
So,
and the audience will post their questions in the chat screen. Some of the audience, if they want to interact with you, they'll raise a hand, and I'll unmute them, and they'll also discuss with you, ma'am.
okay. Thank you.
This
So,
session or
yeah. So I'm just switching off my camera just to save the bandwidth, and I'm going the full screen,
okay.
and I hope it's like visible. So as this talk is on quantum computation, I said image processing, but I kind of these days image processing is mostly machine learning based image processing that we do. So that is why I have little changed the title of my talk, that is on quantum computation and machine learning. Uh, so though I'm doing it in an online way, which is a little difficult to have an interactive, but let's try to have some interaction if possible, and just raise your hands whenever you can, and so that I do not feel that I'm teaching to myself on a laptop. So I just assume that some of you at least have an understanding of quantum computation, but just to kind of give you my perspective of it, what is a quantum computation? So for me, anything that you do on a quantum computer is quantum computations, and uh, and what is a quantum computer, if I then ask? So that is something which is based on the quantum mechanics, quantum physics, and that is what my quantum computers are. Now, what is the quantum physics and quantum mechanics, and how is it different from the mechanics that you have studied till now? When we were in class 7th and 8th, we started studying the mechanics. We studied the law of motion, Newton's law, and all that. They were classical mechanics. But then I mean, are there different laws that govern the universe? And if there are different laws, then how does these classical laws fit into it? So in order to answer this question, we need to go little more in detail. We will understand what is my classical mechanics is, and how is it different from the quantum mechanics. My classical mechanics is actually mechanics of a big particle, of big infrastructure. When we studied in our school, we studied about the motion of a bus, motion of the apple falling from the tree. They are big particles. They are not like a small particle. So their motion and everything is what we studied. But there are particles which are very small, a subatomic particles like an atom, like an electron. They also kind of have a motion. We all know that electron has a motion, which it has a spin in it. It also revolves around the nucleus. So that is a very small particle that we have, a very subatomic particle. They also move. Now there is a subtle difference between the motion of an electron and motion of a big particle. Am I right in saying that? No, I'm not right in saying that. But the difference is, when we talk about a big big particle, big ball moving, I my resolution to understand the position of the ball is different as compared to when I talk about electrons moving. My resolution of its position is different. I go on to a microscopic scale when I want to understand how much is the position, how the position of electrons is changing. Whereas when I talk about the bus, I'm okay with in meters or sometimes kilometers also. That depends upon what kind of a particle I'm talking about. So that is the difference that we have in a bigger particle and in a smaller particle. So now when I'm dealing with the small particles, I need to have a more dedicated way to explain their positions and their velocities, or maybe the momentum, and that becomes a challenge. So this challenge was first encountered and explained by Heisenberg, and he said that there is a Heisenberg principle of uncertainty, that the motion, that the velocity and the position, the momentum and the position, he said, cannot be determined accurately together. And this this uncertainty makes more sense in case of a small particles as compared to big particles. Because in the big particles, my resolution required is not that critical. So that, because it becomes critical, and this principle is what we actually observe and we require. So this is a different mechanics I need to do it. And that is what is known as a quantum mechanics. So if I actually expand it, classical mechanics is a subset of my quantum mechanics, because I am adding more uncertainty with the probability study I'm doing. I'm not talking about exact velocity. I'm not talking about the exact position. So that is what my classical mechanics was doing. So quantum mechanics is a layer above it. Now, but it actually it has those principles and of classical mechanics that it obeys, and I I can use them to explain many of the things. If I look at the history, so we all know that energy is proportional to the frequency. So E is equal to h nu is something which we all know. So my energy is proportional to the frequency. So as my wavelength decreases, my frequency increases and my energy should increase. So this is the graph that I have plotted over here. So over here, x-axis is my wavelength and the y-axis is my energy. So what will happen if my wavelength decreases? My energy should increase as the graph is showing. But then what will happen if I make my wavelength very small? Do I get a complete burnout? I can have a very small wavelength, but does it mean that I will have a complete burnout and a blackout might happen? So the classical theory, according to the classical theory, this should have happened, but we do not observe that kind of a behavior everywhere. I mean, you might have signals which have a very low wavelength and a very high frequencies, but there is no kind of blackout happen. So this is something uh, some facts that we have observed in our life and which we could not explain using a classical physics. This is known as ultraviolet catastrophe. So in order to explain this, the scientists actually went and understood more phenomena around it, and that led to an understanding of something which is known as a quantum mechanics. Now, how do you explain this kind of a difficult phenomenon? This kind of a phenomenon is actually, I'm not going into that much of physics, but I actually get when I understood this, I was very much fascinated because I never imagined that this kind of a behavior might exist. So that is why I uh, would like to start my things in this way. So this fact was actually explained by using a dual nature, that every particle has a wave character and every wave has a particle character. So this dual nature of a wave particle can explain why this behavior that at low wavelength my energy does not become infinite. It becomes my wave nature becomes a particle and the particles have different energies, and I can explain that. So basically this is something which people have observed in using experiments. They actually saw that. I mean, if those who have actually have studied this course, they might have seen this double slit experiment where people actually saw that, prove that electron, which is a particle, I mean, you feel electron is a particle, but it also has a wave kind of a nature. Light is what we know is an EM wave. It's a wave kind of a behavior, but it also has a particle nature. So this dual nature of things that we have around us is actually can only be explained using quantum physics and quantum mechanics together. So this led to a need of quantum physics and quantum mechanics for us, and we went and started understanding more about it. So this is the experiment that I'm saying, that this electron is a particle nature, but at times it behaves as a wave nature also. You see this interfering pattern in the wave-like structure, and if it was a particle, if it passes through a slit, you will see only a spot. So this kind of behavior was experimentally observed, and in order to explain this behavior, people gave a notion of quantum physics and quantum mechanics over here to explain it. So basically, these phenomena, these laws were given to explain things what we are observing in the nature. Now, what we want is we want to understand these phenomena and these principles, and we want to use them for our benefit, so that we can understand them better, and we can design systems which can take the advantages of these behaviors, and can solve our things in a much better way. So now here the particles that we are dealing with is small particles, the particles of atomic and subatomic particles, and these particles need to handle and design our systems with. So as I said, so this is a duality nature of any physical object, which is particle and as well as wave. So when I gave you an example of light. So light is a particle that is known as a photon, and light is also like a wave, which we all know is an EM wave that it moves. So this is actually what I say is the dual nature of all particles that we have. Now, so basically what I'm saying is that everything is having a dual nature. I mean, if I give you, I mean, any other example, we all have dual nature. We are different in class and we are different at home. So I am sure that maybe 100 years down the line, we are celebrating 100 years of quantum, but maybe 200 years down the line, people might also say that the particle or the matter has a third form also, the third nature also, which were not very clear at that time. So because it is what we are observing that it has, and then we are trying to understand it. Now, this is a dual nature, and in order to explain this dual nature, people are trying to understand how we can express this mathematically. So Schrödinger, so there are many scientists or physicists and mathematicians who kind of try to model this dual nature. But finally, Schrödinger's equation is turned out to be a Bible around it. He gave an expression. This is a simple expression. I will not go too much in details in the maths on it, but just an intuition on it. He gave this relation, the Schrödinger equation, which actually explains the dual nature in it. So this psi is my state, and this is a function of my position as well as time. Position is of a particle, and it's a function of time as a wave moves. So it expresses this in a dual form. Now, what I actually have is any system that I have over here, I can express using this Schrödinger equation. This is an equation actually written to kind of equate the energies around us, and using the energies, kinetic energy and potential energies, I define my state. And they're saying that the state can be given by this simple wave equation or a state equation, and it explains the dual nature. Now, this forms the basis of my quantum mechanics. Now, this dual nature is what I want, and I want to use this dual nature in understanding my systems and other parameters around it. Now, what is this dual nature, and how is it going to help me? So those who have studied this quantum mechanics, they might have seen the Schrödinger equation, and they might have tried to solve the Schrödinger equation. So maybe I'll just go, I'll come to these things later. So this system, that Schrödinger equation, can be actually solved in this form. This can be written as a solution to the Schrödinger equation in certain case. Now, what is this solution that I have? This solution tells me that the state of the system at time 0 is this, and then as the time passes, the system becomes psi of t. The state of the system becomes psi of t, and it is actually given by this simple equation. So this simple equation actually governs my system, where this H is something which is known as Hamiltonian. So this Hamiltonian is being defined based on the energy of the system. Now what I'm saying is that I have a quantum system, and this is the evolution of quantum system, which starts with an energy at t equal to 0, and this is how its energy, its state is changing when the Hamiltonian, which represents the complete energy of a system, is h. This is how the system is changing as a function of time. So this equation forms the backbone of my any quantum system. I hope I'm clear. If there is any question, please ask me. So this concept is very important because this gives me an understanding of a quantum system. I am a signal processing person, so I look at this equation in a from a system point of view, that this is the input to the system, and after time t, I get this as an output. Those you as I yours is a AI machine learning kind of a department, so you can look this equation as a complete neural network, where this is the input state of your machine and this is your output state of a machine. So this equation is what we deal every day in different form, but uh, but uh, but in a quantum mechanics, in a quantum computation, this turns out to be in this form. Now what we want to do is we want to have now we want to use this equation and solve our system S. Now there are different ways by which we want to exploit this relation in our for our benefit. As I said that we want to understand quantum mechanics and then use it for our benefit. So what we want is we want to use this equation for our benefit in some way or the other. Now, how do I want to use this in my way or the other? Now, I want to design a system. As a person, what I have is I do signal processing. What is a signal processing? Okay, I have a system. I have an input. I want to do processing on it so that I get my desired output. So can I look at it in this form? I want to have an input and I want to do some processing so that after time t, I get my desired output. So what do I want? I want some edge, my system, to give me desired output. So can I design a system which can do that? Yes. My Hamiltonian over here can give me a system which can give me the desired output. How do I implement? We'll understand a bit later, but this is what I want to do. I can study a system. Suppose I want to study the effect of an input on some system. Suppose I'm a patient and you give me I'm a human being and you are giving me some medicine and you want to see its effect. This is my present state. I model my effect over here and I can see the output. I can use this equation in a quantum base to understand and do my required things in the quantum mechanics. Now, how do I use this? This is I've given you a very basic overview, but if I actually want to do it, how do I do it? Now, this is my state that I'm saying, and this is also another state. Now, what they said that, okay, let's do very simple thing. Let's assume that my in order to represent a state, how do I represent a state? I represent a state using uh, uh, certain vectors. I mean, I have a space in which I kind of represent myself, and the states can be represented as the sum of the bases. I mean, the linear combinations of basis vector. That's how we have been doing till now. I have a point in two-dimensional space, so I say that it can be represented as coordinates in x and y axis. Similarly, what I assume people over here is because this is my present state. I assume a very simple system, that I have a system in which I have only two bases. I mean, a simple, a two bases, two-dimensional system is a very simple system. So to begin with, people assume that you have a system with only two bases, and using two bases, you can represent your states. So that is what you are saying, that okay, my state is very simple state. It can be represented using two bases, and I do some computation on it, and this is my output state. This again can be represented using two bases. So this is my input-output relation using two basis function. A very simple input-output relations that I have made. Now, what are these two bases? These two bases are actually, I will come to this later. So this is what I'm talking about. My two bases are. One base is 1, 0, another base is 0, 1. We all know these are the two. If you have a two-dimensional space, these are the two bases. And I can represent my input and output as I mean any state in two dimension using the linear combinations of these two bases. We all know that. So this is what is quantum mechanics is. This is nothing different. I say that, okay, what I do is I kind of say that now it's just a representation. I say that this is my 0 and this is my 0 base, this is my 1 base. Instead of saying base, I say that this is a 0 cat and this is a 1. So they represent my basis vector that I have, and using these basis vector, I want to represent my any state. Now, what does it mean? I again come back to this equation. This is known as a qubit. This is my present qubit, which can be written as a linear combination of these two. And this is my, but after processing, you get this can be written as again combinations of these two. And because this is two dimension, it is this operator over here becomes a matrix. So this is my complete quantum mechanics in two dimensions. I hope I'm clear. So this is what the basis of my quantum mechanics. So what I'm doing is I'm kind of using my principles of quantum mechanics and defining my operation. I have a input state of I have any input state. It can be a linear combinations of this, and it's my output state, which can be any linear combinations of this. Now the beauty is that my input and output can be any combinations of these two states. What does it mean? This is again a two-dimensional vector, which is also a combination of these two. They represent my qubits. My qubits is actually a linear combination, is also a single qubit. If it can be cat 0, cat 1 and a superposition of them, this can also be my input state. So what does it mean? It means that using single qubit, I can represent how many possible situations? Alpha 1 and alpha 2 can take any value. I put a limitation, that their mod square is 1, sum of the mod square is 1, but even then, there are infinite possible values that alpha 1 and alpha 2 can take. What does it mean? It means that using a single qubit, I can represent enough large amount of data as compared to my classical bit where I was only representing 1 bit. So this is the example. Now I can explain it in a better way, that my classical bit was either 0 or 1, but my quantum bit, it can be 0, it can be 1, but it can be any combinations of that also. My alpha and beta can be complex also, isn't it? If they can be complex, I can represent any amount of I can represent anything on this sphere over here. So that is the strength that we have because of this quantum mechanics, that I don't represent only two states, I represent infinite number of states. Why I do represent infinite number of states? Because of this principle of superposition that is there in this case. Now I can represent using 2 bits, I can represent so much. Now what about if I have n bits together? My uh, I can have more than 1 bit. Suppose I have n bits. So if I have n classical, sorry, if I have n classical bits, then each bit will represent either 0 or 1. And if I have n bits together, I mean, we all know that we'll have a 2n possible combinations. But if I have a quantum bit, then what do I have? With, it's a superposition. So I can represent all So this single, so n bits, n classical bits can represent one of the possibility, isn't it? But 2n quantum bits can represent all possibilities with different scaling factor. You can have because it's a superposition. At a time, you can be 0 or you can be 1 or you can be in a superposition. Sometimes, I give an example to explain this, that I'm always flickering in mind. I do not know I'm 0 or 1. When I go to the market and I want to buy a dress, I do not know that shall I buy it or shall I not buy it. So I'm always flickering in my mind. This is actually the correct thing. This is actually our mind is. So this is what my quantum bits is. I can represent this using all the 2n possible combinations can be represented all together using n cubed. So this is the power that we have of our quantum systems that we have with us. So, uh, so this is like maybe I can skip this. I go to the next slides. I think now this is more important over here. Now this is though I said that I can represent anything, but now how is it possible to realize a quantum computer? Now let's just try to understand that also before we move ahead. How do we represent, how do we make our classical computers, the computers that you have, and I mean the computers, the phones, how they are made? They work on a principle of input bits and output bits. And when we have an input bit and output bit, you have a circuit. And the circuit output, if it is 0, it is 0. If it is 5 volt, it is being called 1. Anything in between 0 and 5 is you have a threshold, above the threshold, below the threshold. That is how you define your bits. But you always know that the signal can be in between. Suppose the threshold is 2.5, so the signal can be in between 0 and 2.5, and signal can be in between 2.5 and 5. The signal can be in between, but still you call it as a 0 or 1. So basically, that the states exist in between, but we were not using it. So that is what people are tapping now. That can we use those states also with us? That is what my quantum states are, a combination of 0 and 1. So, I mean, possibly suppose you have E field and M field. In actual practice, I work in a combination of that. I can represent E field as say 0 and M field as 1. And if I have a combinations, I am in a combinations of that. So this is possible. So that superposition actually gives me the representation in a viable way. In fact, I mean, the electrons also have two spins, spin up and spin down, their motions, their everything. So people are working on different ways of realizing the qubits. That how can I have a qubit which is a combinations of 0 and 1? Now I want to represent my qubit as my representation. I want to represent qubit as some number. I have my speech coming. So I want to encode my speech into qubits. So basically, it can be any value. How do I represent? So it means that the states that I'm saying, if I say that electric and magnetic field, so I want that electric field 50%, magnetic field 50%. That gives me 1 qubit. When I process it, I change my electric field to something and change my magnetic field to some other thing. But that control I want on it. So what is the best way to get that control, and what is the best way to represent the qubits? That is what people are debating these days. Okay, what is a good qubit? People are working on a different technologies of superconducting loops, trapped ions, photonics, many kind of structures people are working on, and they are trying to design their qubits in a much better way. But what we are interested in, we as a signal processing, as a computations person, as you are like AI machine learning thing, we are interested only in the applications of it. So let me just go ahead and I think I have made the base clear. Now let's just try to understand the applications. I just skipped this. I'll just spend 2 minutes on this. So now, how do I design my applications on it? What is a quantum computer, and how is it made from? What it is made from? I've given you a complete like a flavor of it, that it can be made from different technologies. The technologies which are present with us in many forms, it can be made from that. But now, how do we use that technologies? So when we discussed about, when you studied about computers, how the computers were made. So you all remember, I think, we had some gates, digital gates, and my digital gates made my digital computers. You know that the NAND gate is the universal gate, and using that NAND gate, we could get all the operations done. So that is what my digital gate is, and it can do all the operations. Now, similarly, what we have is, we have in the quantum thing, we have the quantum gates. I mean that's we want to build a quantum computer. My quantum computer will be analogous to my classical computers. So we have bits over there. Over here we have a qubits, the analogy. So there we have the gates. Now again we have a quantum gates. But the difference in the quantum gates and my classical gates is, my quantum gates takes the qubit as an input, and the output will also be a qubit. So basically this is how I kind of represent my quantum gate, that my input is qubit and output is a qubit on it. So what is a qubit? Qubit can be, if I talk about a single qubit quantum gate, so that I have a I have some qubit which can be seen as a linear or superposition of these two numbers. So this is my input qubit. I do some operations on it and I get my output qubit. What is this? This is just a simple matrix multiplication, isn't it? So my all quantum gates are nothing but a matrix multiplication. I have my input operations. So this is an example of a single qubit gate. I have an input state and I have an output state, and this is my gate. Certain properties these matrices should fulfill, but in general, if I just say in a layman's language, this is nothing but a matrix operation. A 2 cross 2 matrix represents my single qubit gate. Very nice. 2 cross 2 matrix represents my single qubit gate. So what about, can I, when we started studying gates, we studied a very simple gates, AND gates, NOT gates. So what is an AND gate? Okay, what is a NOT gate? I am talking about a single qubit gate. The first gate that comes to me is a AND gate. So what is an AND gate? AND gate means that if you have a qubit which is in a superposition of 0 and 1 with the weight alpha and beta, my NOT gate will flip them. Okay, so it means that it will flip 0 to 1 and 1 to 0. That is what it is doing. It is flipping 0 with the weight alpha, it is making 1 with the weight alpha. Beta with the weight, 1 with the weight beta, it is making 0 with the weight beta. So this is my quantum NOT gate. This is actually denoted by X. Now, in order to represent this NOT gate, I kind of represent this using this simple X matrix. So this operation is my NOT gate operation. Are you with me? I mean, does it make sense that this is my NOT gate? I somehow, online you don't know how is your reaction. Otherwise, I mean, looking at you, how you are feeling, we can sometimes gauge that do we need to repeat or not. But I'm just assuming that you are understanding what all I'm saying. So this is my NOT gate that I have. This is a single qubit gate. Now, various other combinations are also possible. I mean, so that is how people have designed various gates. So this is my X gate. This is my Z gate. My Z gate means what? If I have 1, it gives me -1. If I have 0, it gives me 0. Another gate possible can have any possibilities. I say that, okay, I have 1 because I said alpha and beta can be complex. So another gate. If I have 1, I get 0 iota. If I have 0, I get 1 iota. I can define any other gate, X, Y, Z. All the gates are possible. In fact, I can even rotate the gate. So if I have 1, I rotate. If I have 0, I get 0 only. I mean, this is a phase shift gate. So there are possibilities of gates, and all these gates are possible, and these operations I can do on a single qubit gate. I can rotate only on z axis, only on one axis by some angle theta, and another axis by angle. I can do anything over here. So this is a simple rotation gate that I have a 1 and I'm rotating it by angle theta. I have a 0 and I'm also rotating it by angle phi. I can do whatever in my qubits over there using this matrix multiplication. Only thing is, I think you might have seen by now is this matrix which is working as a gate is a unitary matrix. The norm of this is 1, just to keep the energy constant. Let's not go into that much of detail, but I can define a 2 cross 2 matrix which works on an input qubit and gives me an output qubit. This is possible. This is an input-output relation, and what I'm doing is I have a matrix only. This is what I've seen because my input is a two-dimensional space and my output is also two-dimensional space. In between, I have a 2 cross 2 matrix. This is for a single qubit gate. Yeah, thank you. So any operations can be done on a single qubit. Now, what about 2 qubits? What will happen if I have a 2 qubit? What is an OR gate? My OR gate is I take 2 inputs and I give 1 output. Okay, so some kind of analogy difficulty, but the difficulty over here is the way the circuit is being designed, the dimensions are not changing. Remember the equation that I had over here? Maybe I can go back and show you the same equation, which is a Bible of, I just kind of didn't explain you these things, but I hope that is okay. My story will be again going into different direction. So this is the equation I said. The state over here and the state over here have a same dimension. It is not changing. As it is not changing, I cannot define a operation which is of different size. My qubits, which I have, my states, should be in the same dimension. My input state and my output state has to be in same dimension. So number of qubits that I take in input and the number of qubits that I take in output should be same. Some kind of weird thing that nature has kept on us, and because of that we cannot define 2 qubits gates which are uh, uh, we cannot define 2 qubits. I have discussed, yes, we cannot define 2 qubits gates which are uh, which have only single bit output. We have to define 2 qubit gates which has 2 qubit output. So this is a simple 2 qubit gate which takes 2 bits inputs and it gives 2 bits output. There is no gate in quantum mechanics which takes 2 qubits and give 1 qubit as an output. It is not possible over here. So this is a kind of a difference that we have in case of my quantum mechanics system as compared to the classical system, that I have the gates which are not I mean, the gates are of the same size. It can be given by a square matrix. And what I have over here is, I also have another reason that these gates are reversible. These gates are always reversible. I mean, now this is my C naught gate, which actually is same as XOR gate. Those who have kind of working in this area may have kind of recognize this thing. So over here, what happens is, I mean, the philosophy is that if B is 1, this B qubit is 1, my A qubit will be flipping. So if B is 1, A gets flipped. If B is 1, A gets flipped. So and B remains the same. So this is what you have. So you are actually doing XOR on A only, but B is just kind of you are getting an output because you wanted it to be of a similar kind. So this is my quantum gates that I have. I can have similarly, I can have large number of large number of quantum gates also, but the requirement is my input bits should be same as the number of input bits should be same as my number of output bits that I have. So this kind of an understanding I should keep in me in order to design my quantum gates. That is what the mechanics is imposing on me. So basically, what I have only a matrix, square matrix. It's an Hermitian matrix. That's something is also, I said a unitary and a Hermitian. I'm using these two terms. If it is not clear, don't worry. It's just a matrix, 2 cross 2 mat. It's like a whatever is the dimension, it's a square matrix. What I want is the determinant of it should be 1. Why? Because I just don't want energy to be playing role over here. Also, I want it to be invertible. That's because I can invert and I can go from here to there and come back from here. So these are the 2 requirements that I have, and I can design any gates in the quantum system that I have. So this is actually a system complete quantum operations that I'm doing. That okay, I have these gates. I mean, this UVW are different kinds of gates that I perform. I have different inputs, and over here I get an output. Now comes a very difficult question that we need to understand. If you see, I said the quantum number that I have is in between. It can be a linear combination of 2 states, 0 and 1. But does this linear combination make any sense to me? I said that I am going to a market and buy a dress. I'm in a double mind that do I buy this or do I not buy this? Shall I buy this or shall I not buy this? Does this double minding thing is giving me any benefit? It might give me a benefit while taking a decision, but I need to take a decision and use that, isn't it? I mean, your neural network, you need to have a hard decision, only then you get an output. So that is what happens even in the quantum systems also. You have to kind of work on it and take a hard decision. And this hard decision is known as measurement. From a quantum domain, you come to a physical domain. and give a result to us so that we understand this. So this is a basic phenomenon of measurement that is also done, that is also part of my complete quantum system. Now, what is a measurement mean? Suppose I start from 0 and 1. So this is my 0 qubit, this is my 1 qubit. I do certain operations on it and I kind of end up my these uh, uh, 4 states, and then I again do certain operations on it and I have these possible outputs. But in the end, when I actually want to represent my result, I again need to go back to my 0 and 1 state in order to make uh, in order to kind of make some sense to me so that I can represent my numbers to the word and the word can understand. So this is known as a measurement, which is again kind of important because it connects me to the classical word and I can use this better in my sense. So this is what I kind of discussed about the basics of the concept over which we can build on any system. How much time do I have? I have not kept.
Ma'am, half an hour more.
Okay, good. So now I kind of want to give you something. How do we use this quantum systems and quantum things in day-to-day life? So let me skip few of the slides and uh, come to something which will be actually useful for you being a, machine learning and people. I am just skipping. Okay. Now, till now I said I have a 0 qubit and 1 qubit. How do I use this 0 and 1 qubit in my day-to-day life? As I said, I have a signal that I want to play over here, and I want to process it. So my signal, I have a music to process. What is my music? My music is a complete signal. So I need to give this signal to my computer so that it can process it. How do we do it in a classical domain? We take a signal, we sample it, we quantize it, and that is a digital bits we get, and we can process it. That is how we have been doing till now. How do we do it in a quantum domain? It means the sample that I get, I need to represent using qubits, isn't it? So means if I have a music coming to me, I was representing it as a series of bits. Now I need to represent as a series of qubits, so that those qubits when can be processed by quantum computers and I get my computation done on it. But how do I represent my input as qubits? Qubits are the states. But I need to do something. This is a thing which is known as data encoding. And anybody working in this quantum area and any algorithm you want to try, this becomes an important thing. So I thought I can talk about it now. Now, there are various ways by which you can do the encoding of your thing and use the quantum. So what is the simplest way by which I can convert my music into qubits? What thing that comes to your mind that it is possible to convert my music into qubits? I know how to convert music into bits. Do I know? Yes, I know. I just told you I sample it. At sample, I quantize it and I get my music. But how do I convert into qubits? So one person, we start with very basic thing. So the basic thing is, okay, you have series of bits, replace it with qubits. So that is what is known as a basic thing that, okay, if I have bits, I replace by qubits. So this is, I am giving you a number. Suppose I have 2.3 as a number, as an amplitude, which I want to encode. So 2.3, if I want to use 3-bit representation, it is given by 0, 1. This is the 3-bit number representation. That suppose I say. This is the binary representation. Okay, this is a binary representation. Convert each bit into qubit. Okay. So I require, whatever is this, I require B qubits, 6 qubits to represent this. Does this make sense? Yes, it makes sense. I could represent my data into qubits and I can use the quantum computer. Any flaw in this? I am using 2.3, one number, and I'm using 6 qubits to represent it. I just said each qubit has immense power. It can represent anything. Remember, I said n qubits can represent maybe n qubits can represent so much together. But now I'm using so many qubits to represent only a single number. This is an overkilling. One should not do that. So people just thought, okay, when things come, you just use it in a possible way. When the computer came, we started using it for multiplication. That's how it is. So this is something which we thought we can do it, but this is not good. Then people became educated. They said that this is an overkilling. So they decided another way of encoding the things over here. So this is uh, like what do we do? So they said that, okay, suppose you have two data points. So one data point is this and another data point is this. So what are these two data points? This is like, if I look at the places, this is like 7 and this is 14. Okay, so I define a vector like this and I say that, okay, this is at this is 5 and this is 14. So this is at 5th position and this is at 14th position, and that is my data over here. This is another way which is possible. Now I require less number of qubits possible. I do not say that I am using, I am using a large number of, but still it's a large number of bits that are possibly used over here. Then people define another way of encoding the data, which is known as amplitude encoding. As I said, a qubit can represent a superposition. So people try to use the superposition. So suppose you want to represent these two numbers. So one feature, you are doing a machine learning work with you. So suppose you have two features as an output. So this is one feature, this is another feature, and you want to represent these two features using qubits. So as I said, these are two numbers, and I want to represent using qubits. So what they did is these four numbers, they appended into a vector. So 0.2, 0.5, 0.2, 0.1, they made one vector. They normalized it. How did they normalize? So they evaluated the norm of it, square norm of it, which turns out to be 0.34, and they divided it by this, so that this vector has a norm 1. Now, if this vector has a norm 1, it can be represented as an amplitude of a 2-qubit system. Is it clear? So I can represent this two features using 2 qubits. Think, this is not possible in the classical system. Even to represent 0.2 and 0.5, I require large number of bits. But over here, I am representing the complete data using 2 qubits. I could do that. This is what the strength and the power of my quantum systems are. I can do the amplitude encoding over there. Now another thing is, which is, I hope it is clear. Another thing is the angle encoding. So what is an angle encoding says? Okay, I can represent, I can represent any point as a rotation. I say that, okay, I normalize it. Okay, I just go over here again. I'm saying that this is a amplitude of this. But can I, because they are normalized, I can assume that they to be an angle. And I can represent this 0.34 as some rotation, 0.86 at some rotation, 0.34 as some rotation, 0.17 is some rotation. So I can represent this data using 4 qubits, which is again better than my classical thing. So these two encoding schemes are very popular and are being used tremendously in most of my quantum computation systems that we are doing. We generally represent the data using either angle encoding or amplitude encoding. You might have seen that in most of the things that you see. So this is another way of encoding the data, that okay, these are my initial bits and I do the rotation and I represent my data over here. Now the third and important thing is my image representation. How do I represent my image? How do I represent my image in a classical domain? I have RGB image, and in order to represent my RGB image, what I do is I have intensities of R, I have intensities of G, and I have intensities of P. And these intensities is what I use in representing the image. Now, these intensities these intensities is what I have are of R, G, and B. Now, can I somehow combine them and represent using one? This is what I use it over here. I remember we have seen what is the color of a light. The color of the light is given by the frequency. We all know about it. And what is a frequency? Frequency is just a number. So what they say is that, can I represent color by the frequency? I don't have to represent RGB, the intensities of RGB. Instead, I give the color by a frequency. So if I have 4 pixels, this is one color, this is another color, this is another color, this is another color. I do a normalization and this becomes my angle. And this becomes my image representation, which means that I require only single qubit to represent my color, unlike my classical thing, where I had RGB intensity. This saves so much of, the representation is so compact and so better. And I'm not losing on anything because I'm representing completely. The frequency is a unique representation of the color. I'm doing that. So I can get a better representation and I can do good things over there. And that is what my quantum things are doing. So now, how do we have a complete circuit? If I want to do some image processing on it, I suppose I have a 4 pixel image. I'm a very classroom kind of an example. Classroom in a quantum sense, that I have 4, because the number of qubits are limited. Suppose you have 4 qubit system. You give input as a qubit. You do the processing on it. And this can be the processing. I mean, any processing. This H is also in hard mart gate. I mean, there are many gates possible. So I didn't discuss about this, but this is also a gate which I do it. These are my input qubits, and I can do the processing the way I have been doing and do it. So part of this processing, which I am doing now, is for my representation also. Because what I have is I assume that okay, my input signal is being represented into qubits. So what I assume is that these inputs are 0 qubits, and I do this rotation to represent my data on it. And then after that, I do certain operations on it to carry out my tasks on it. So this is a simple input output relations, a simple inputs output circuit of my quantum system is. So I have kind of given you an understanding in this thing that how do we do processing in my quantum system. So what I require is I take an input, I represent the input in the quantum domain. It can be amplitude encoding, it can be basic encoding, it can be angle encoding, it can be image encoding, and there are various other encodings also possible. I'm just giving you an overview over here. So it's possible. Then I perform certain tasks. I use those gates to do those computations on it. And after that, I take a measurement to give my results to the classical world. This is a complete system that I design in my quantum world. So what I mean, I want to give you an example that is possible. So suppose I make a very classroom kind of an example that I have two images and I want to match them. I want to match how much is the similarity between these two images, pixel by pixel. Suppose this is like 4x4 image, and I want to see that how much is this image matched with this. So this, if you compare these two image, this is a black pixel, whereas this is another color. So these two images are not matched with respect to this pixel, but otherwise all other pixels are being matched. So what I can do is I can just compare, I can design a circuit which compares this in a quantum domain. I have done a FRIQ representation, the frequency dependent representation of this image. I have a frequency dependent representation of this image. I just compare the angle because each pixel is being represented as a frequency. I just compare using the frequency, which frequencies are not matched, and I say this is kind of unmatched. So I can design some algorithms which work on a quantum domain and do the desired task. Another good example of this is machine learning, because you all are AI thing you've done on a machine learning. So what we want is my quantum input and my quantum output. I can do that. But the challenge these days is the quantum computers are not of given strength. We have a very small size quantum computers with us, and it becomes sometimes kind of difficult. Still the technology is in nascent stage till we get it. So real power is not there. So what people are doing it, they are using a hybrid quantum machine learning where they use the classical network and they have a quantum layered in between and get the output. I mean, people are trying to make a complete quantum things, but still, it's because of the available qubits are less. I mean, not everybody has an excess of real good quantum systems, and those systems are also very noisy. I didn't discuss about that, but they are very noisy. So people do not have that access. So people have only a limited access of it, and that is what it is. So this is my the kind of networks that we have. So it's kind of an transfer learning, or you can say a hybrid network that we have. You have a classical network, you train it on a classical thing, and you have a quantum network which you train. Again, you have to map your classical input to the quantum and then again come back. So this is the kind of networks that are possible, and this kind of a networks is what we are also working on. You kind of design the circuit, and over here you again do the similar way of training as you have been doing in a classical thing. You have those gates, you kind of work on those gates parameters, because remember, what is a gate? Gate is just a matrix. So you just kind of train to tweak on those gates parameters and get the desired result. So, I mean, some of the results that we did at on, I mean, we tried to train using MNSIT database, which is very commonly available, and did it on a quantum things and got some results. But still, it's just a kind of an exercise which says that okay, this is possible on the quantum, but we are still not able to tap the complete power of the quantum things, because it is much more powerful. These are just the toy examples which people are using to understand it. Similarly, some signal processing stuff, some wavelet, some transforms is also possible. I mean, we did it on something on ECG signals classifications. We could also do on the quantum circuits. So basically, this is just a demonstration that some things which we could do it on a classical systems, we can also do it on a quantum system. But I'll say that this is not the real thing which one should aspire for. I mean, this slide is what I kind of like it too much, because this simple problems is what we are trying to solve now. There are certain problems which we are not able to solve in a classical domain. Those problems can be solved in the quantum domain. So the quantum real advantage we need to tap to solve those problems, and this power can be exploited in much better way. As so there are certain representations which are giving us the advantage, but now we have to use those representation to design some algorithms which can use their advantage in a much better way, and we can get a good kind of an outcome in the real for the real world problems which are very hard, like NP hard problems can be solved in the quantum domain. So the challenges that we see in using this is the hardware. As I said, the all the hardware is not available for everybody. Moreover, the qubits, though I have given a very good picture, I think so, but the qubits are noisy. I mean, though I say that I can be in superposition, but to be in that superposition, how much time I can be in that superposition, it's very difficult to say. Physicists are working to have a good coherence time, noiseless qubits, but time only the time can tell when can we achieve that. Until then, it becomes a real challenge to get a real flavor of things that we are doing. But as a machine learning person, as a signal processing person, we should be equipping ourselves with all the understanding and make ourselves uh, uh, available, make ourselves rather ready when those systems are there, and we can use them in a much better way. So my group, we are working on various aspects of it. Some aspects I couldn't touch because of, I mean, it's a 1 hour talk, 1.5 hour talk. I mean, you cannot go much details into those things, but there are certain aspects which we are working on. My basic interest is to use the power of quantum things in signal representations, and I feel it has immense power in representing my analog signals in a much better way, and also to kind of tap the quantum kind of in my optimizations, and that is what we are working on. And as I said before, we are always happy to have people who wants to work and understand things, and we are open for collaborations, and students who wants to do PhDs with us. I mean, I know these days most of the students are in the startup, and they want to kind of earn money, but you know the basics. If you spend time on a problem for a long time, that is what a PhD is, and that patience is what you can learn in a PhD in a much better way, and that is what is required to make a real system work for us. So if anybody is interested, we are always welcome, and I'm happy to discuss over here and maybe after the talk also. Yeah, so that is all what I wanted to say. Am I there?
Ma'am, there are few questions posted by the participants in the chat. Shall I read the question, ma'am?
Maybe I will just open the chat.
Yes,
Uh,
yes, yes.
Okay, how can quantum image processing algorithms such as image filtering, image compression be optimized to achieve significant performance over? Okay, see, image compression, as I said, these representation which I have discussed is about the compression only. If you see, one qubit is giving you the color. Wherever in RGB, you had 8 bits for R, 8 bits for B, and 8 bits for G. So this is my compression that is possible in the quantum domain. When your image is represented in a compressed way, your things is also the kind of processing you do will be much lesser on it. In fact, what people have claimed also, and we have also found that the training of a network in a quantum domain is it takes less time because the features are represented in a compressed domain. You don't require that many bits to represent the complete data. So as the uh, number of bits you requires is less, you kind of train it better. You are compressed. So that is possible. Yes, those challenges of qubits, coherence time, and the noisy qubits is there. But I'm sure the technologists who are working in that area will define ways to make a, qubit stable and also lossless. So otherwise, these error correcting codes and other things also will work to make it in that sense. How can we improve encoding techniques using the practical use cases? Actually, the practical use cases, I actually didn't understand much about it, but you are saying that encoding techniques. So encoding techniques is something, we have to understand. So there, what I feel is we need to go back to the physics and understand the basics, uh, uh, the way people said that the frequency represent the color. Can I represent a frequency as a single qubit? It's kind of an understanding from the physics that we get. So we have to go back to the physics and understand. Now, I give you another example. Suppose they are saying that the qubits can be represented by electron spin. My electron can take a spin up and spin down. People are saying that the qubits can be represented using EM waves. My EM wave, I can combine them in any possible ways. I can have superposition in infinite number of ways. So I have a different representations that is possible. Now, depending upon my application, I use my representation and I can define my tasks on it. Now, representing classical data into quantum domain, I think it's still an open problem in a more optimized sense, and we are and people will be as we evolve over here, more things will come into it. I just gave you a two-dimensional representation of qubits. There is more to it, which I think I could not include to kind of not make a haphazard thing. But this will definitely be kind of there when we go ahead and understand more about qubits. Uh, I can share my email ID. That is perfectly fine. Uh, okay. Angle encoding, you are asking me to explain. Okay. See, the angle encoding is very simple. What I said is that we have normalized the amplitudes. When I normalize the amplitudes, I can each angle, because it's like I can assume that the angle is in radians, and I can give that, or any form, I can just assume that if I use that as an angle theta and I rotate uh my qubit with that angle, so that is my angle rotation. So I instead of I input 0 bit, I make a gate with the rotation theta. This is my angle encoding. Rotation by an angle theta, and angle theta depends upon my normalized amplitude. Because why normalized? Because that is how, otherwise you will not, you want a normalization from 0 to 90, or you can do a normalization from 0 to pi by 2 or pi, whatever. But I want to represent that as an angle, and that is, then I just represent it as a rotation. So this is my angle encoding. Mhm. I think that's all, or is there any other question which I have missed?
Ma'am, two more questions. Whether qubit can have high impedance ZZ and don't care state as well. Qubit can have high impedance Z state and don't care state as well.
I don't have any idea on that. This is something maybe somebody who works in a physics of it can explain. Um, I I need to think about it. Maybe I'll just note down this question and will answer to you. Maybe I'll just write to ma'am and understand this. Thanks for this question. I have no idea. I'm just learning, quantum, and I kind of like giving these kinds of talks because I get these kinds of questions which can make me understand a bit more. And also, uh, I mean, I kind of interact with you and understand your uh, things on your status and your objectives on it.
Any other participants, do you have questions? If you have questions, if you just press the raise hand the button, I'll enable your mic.
Yeah, you can. Maybe that will be good.
Yes, ma'am. Yes, ma'am. Wait for another 2 minutes.
Yes, yes, yes.
Yes, Sweta Rana. Yes, madam, please proceed.
Ma'am, I want to know about the research topics in this area, quantum with the machine learning.
Okay, so there the research is, open in that area, in the sense, one thing is that we want to first understand that how can we use these quantum computers in the machine learning. Presently, we can, as I said, these are the gates only. So we define different kernels. If you are a machine learning person, we have different kinds of kernels. Which kernels work for these systems, and how much computations that we can do uh, on these kernels. What people have found that the kernels are very compact in the quantum domain. The kind of learning you do is also very compact in quantum domain. the applications that you have in AI domain is also on the quantum domain. You can do it. The what you are doing in your CNN, the same thing can be done in a QML in a much comprehensive way. So that is something which is very useful, and can, because you don't have to kill that much of time with you. That is what is being done. Then the variational encoding is something which is possible in the quantum domain, which is also people are kind of working on. So what is that you doing on? Maybe I can.
Actually, I am a scholar, research scholar.
Okay, okay. So what are you working on?
I'm actually now working on cloud with machine learning. Some algorithm, make it hybrid algorithm.
Mm-hmm. So these people are this federated learning and all that, which people do even in machine learning. People are trying in the quantum domain also, the edge computing and all that. See, it's a power that you have, and you can do more processing. The quantum advantages that you can get.
Okay, ma'am. Thank you so much.
Ma'am, I think there are no other questions. Shall we wind up the meeting, ma'am?
Yeah, sure. Thank you. Thanks a lot for giving me this opportunity, and uh, I mean, bringing so many people here. I mean, it's like wonderful talking to you. And yeah, thank you. Thanks a lot.
Ma'am, on behalf of Carolina Institute of Technology and Sciences, I extend my heartfelt gratitude for your enlightening session, ma'am. Your deep insights and expertise have greatly enriched our knowledge, and we truly appreciate the time and effort you invested in making this session valuable. We look forward to future collaborations. Thank you so much, ma'am. Thanks a lot for sharing the inputs. Thank you.
Thanks a lot for listening to me at this time also. And
Yes.
I kind of
I'll
thank
be
you.
in touch. We'll be in touch with you, ma'am. Thank you so much.
Thank you. Thanks a lot. Yeah, bye. Good night.
Good night, ma'am. Ma'am, you can disconnect. Thank you. Participants, yeah, we'll share the contents with you, the PPTs with you, and now you can mark your feedback in the feedback link already. It is shared. Both feedback, both sessions feedback, you can mark it in the single form itself. While you go inside this form, there are two feedback sessions that are available. So you can directly fill the feedback form for marking your attendance. So in this day, there is only one feedback form which contains two sessions feedback. Thank you all. After filling this feedback form, you can leave from this link. Thank you so much. Abhay could you please write a mail stating that what was the mistake that you have done? Will inform them to find out. Abhay Borde. Could you please write a mail? Okay, sir. For ID, okay. By mistake, if you didn't write your ID, at least if your name is there, they'll map. No worries. Thank you. I hope you all have marked your attendance. I'm just winding up this meeting today. C and Sujata ma'am. CN Sujata, ma'am, do you have any doubts?
Hello.
Yes,
Good
ma'am, please.
Am I
Good
audible,
evening.
madam?
Yes, ma'am, you are audible.
Thank you very much, madam. You are providing very good sessions for us. I'm new
Thank
for this topic, quantum computing.
Thank you.
Actually, because of some reasons, I missed 2-3 sessions from the starting. So
Okay,
can
ma'am.
you provide the recording session so that we can follow? Because it is very interesting. Without knowing the previous session, it is becoming difficult to follow the present. So that's
Okay,
why
ma'am.
I'm keep on posting, requesting you.
Okay, ma'am.
Will it
Okay, sure.
possible to share today so that we can follow that one videos and whatever content covered in the previous sessions to follow the
Yeah, sure,
upcoming
sure.
sessions?
Yeah, ma'am. Sure, ma'am. Sure.
Thank you,
Okay,
ma'am.
sure, ma'am. Thank you. Please mark your attendance and leave from this link. Kindly mark your attendance. After that, you can leave from this link. Previous link cannot be posted again here. I'm closing this meeting. I hope you all have marked your attendance. Thank you all. Thank you.